Imagine for a moment that you're floating in the vastness of space. But hold on, that's a bit too extreme and abrupt. Let's tweak it a bit. Picture yourself stepping into the shoes of Cooper from Interstellar, hurtling towards the mysterious pull of a black hole. As the black hole looms ever closer, you desperately call for help from the space station, only to be met with a chilling silence as the transmission fades into the void. What will happen to your body? Is there any hope or survival? The term black hole resonates with an eerie perplexity, conjuring notions of cosmic emptiness and an inherent danger that bursts into the forefront of our imagination. It hints at a celestial enigma capable of pulling us into its abyss, where the normal flow of time crumbles and mind-bending qualities dance on the edges of comprehension. So, what precisely is a black hole? How can an entity that is essentially an invisible void, marked by an overwhelming density, possess such profound significance and gravitational burstiness? The answer lies in the cosmic dance of gravity, where the remnants of massive deceased stars collapse into an enigmatic singularity. In contrast to its name suggesting darkness and emptiness, a black hole isn't a vacant abyss, but rather a space densely packed with an immense amount of matter. Einstein, in his theory of relativity, envisioned the formation of black holes. When a colossal star concludes its life, it bequeaths a smaller core, and if this core's mass exceeds 3 times that of our sun, gravity prevails, transforming it into a black hole. Don't be misled by its name. Think of it as an enormous concentration of matter compressed into an extraordinarily small volume. Picture the sun with a gravitational pull 28 times stronger than Earth's. Stepping onto the sun would render you 28 times heavier than on Earth. Now, envisage compressing 4 suns into a space merely 15 miles, a distance covered in a short 30-minute drive. The gravitational force in such a compact region would be astronomical. In the realm of a black hole, gravity is so potent that not even light can escape, rendering it invisible to the naked eye. However, the gamma-ray bursts emitted by the black hole provide detectable traces, offering a glimpse into its invisible yet powerful presence. Plunging into the gravitational abyss near a black hole introduces a cosmic phenomenon known as tidal forces, aptly named due to their resemblance to the gravitational interactions that mold ocean tides on Earth. As you approach the black hole, these tidal forces intensify dramatically. Imagine the gravitational pull between the moon and the Earth causing ocean tides. Now magnify that effect immensely. The peril arises from the significant discrepancy in gravitational forces acting on different parts of your body. Proximity to the black hole amplifies this difference. The pull on your feet becomes exponentially stronger than that on your head. Initially, the sensation may not be uncomfortable, but as you venture further, the stretching effect becomes increasingly severe. Astronomers vividly term this process spaghettification, an evocative description of your body transforming into a long, thin strand, much like spaghetti. The onset of discomfort hinges on the size of the black hole. In the daunting embrace of a supermassive black hole, tidal forces become noticeable around 600,000 kilometers from the center, a revelation that occurs only after breaching the event horizon. For those free-falling toward a stellar black hole, the uneasy stretching commences at a mere 6,000 kilometers from the ominous core, presenting a cosmic spectacle long before crossing the point of no return. Spaghettification is not inevitable. Black holes of different masses will have different gradients. So with supermassive black holes, it is perfectly possible to pass the event horizon with no ill effect. Again, this is not to say that the gravitational pull isn't strong, just that the gradient isn't too extreme. Let's assume this is the case. Unfortunately, other stuff seems to be falling into our black hole too. Although a bit of company might seem welcome, infalling particles spiral into the black hole in a turbulent flow, rubbing up against each other. As we've seen, the accretion disk formed emits radiation due to this friction, and because of the immensity of the gravitational pull, Particles are accelerated up to significant fractions of the speed of light. So imagine falling into a black hole one more time. Things get really weird because the black hole's strong gravity messes with time. This is called time dilation. Let's say I'm on a faraway space station trying to help you. From where I'm watching, it looks like you're slowing down as you get closer to the black hole. According to my clock, time is moving way slower for you than it is for me. Now, as you get really close to the black hole, something even weirder happens. It seems like time almost stops for you when you're near the edge. It might sound strange, but time isn't the same everywhere. Objects move through both space and time at different rates, and this strange situation we've set up shows that. It might be extreme, but these time changes happen all over the universe, just not as dramatically as near a black hole. If everything else was fine, you'd simply pass the event horizon and keep going towards the singularity. Of course, the words fine and simply are doing a lot of work here. What's happening outside the black hole while that's going on? Well, sadly, I've had to give up on being able to reach you or even get a signal from you. You've passed the point of no return. From your point of view, there is no outside to reach anymore, since every direction leads you towards the center of the black hole. From my point of view, and to all intents and purposes, you've ceased to exist. This is why black holes are just the end, both in space and time. Effectively, things crossing the event horizon play no further part in the universe. They cannot signal anyone, and vice versa. And when we say signal, we don't mean sending a coherent message. We simply mean transmitting any information at all. As it's crucial to remember that these are theories, not certainties. While we lack concrete proof, the calculations and structures supporting these ideas are robust and validated within the realm of theoretical physics. In simpler terms, the science behind this is sound. However, attempting to hurl yourself into a black hole isn't and wouldn't be sound. But sure, something to imagine.